Right. Good afternoon, everybody. Good morning, everybody. My name is Neil Stevenson. I'm going to be talking today on remote caches. My email address is there, neil@hazelcast.com. If you think of a question after the Q&A, just drop me a line. So I'm going to be talking for just short of 45 minutes today. Leave some time at the end for questions. There's the outline. Let's get straight into it with who am I? So once again, my email address. There's a bit of a clue. My name's Neil Stevenson. As my guest, I work at Hazelcast, where I'm the principal architect. I've been developing for 30 years, a bit more actually, but once you're into the 10s, 20s, 30s, the preciseness doesn't really matter. Last 20 years, been pretty much Java. I've reached the standard of average, I would say. It's learning all the time. We'll see some of my code later, so you can make your own judgments. But really, the point of today is just to kind of think differently on what a cache actually is. So what is a cache? So kind of the typical definition would be something along those lines: small, fast, local, temporary copy. And that's absolutely true for things like a level 2 cache on a computer chip, a CPU, and you might be caching various things on websites or application programs or all sorts of things. So there's nothing wrong with that definition, but it kind of excludes certain things. And really, when we're thinking of applications, we're not going to bother with computer chips today, but you're going to have data in some sort of store somewhere, relational database or whatever, sitting on a disk, and your code needs it, so it fetches it from the disk, and that takes a certain length of time, and then it needs it again. So if you've got it kind of to hand, then it's faster. And really, speed is what it's about. Faster, otherwise you just wouldn't bother. So speed is the thing that matters. Small, fast, local, temporary copy, no, it's fast. And really those other things on something like what we normally think of a cache, they're kind of trade-offs. These are things that we're going to deal with just to accept the fact that we're going to get that data faster. So, small, well, it's a local copy, and that means it's sitting on smaller storage for some reason. And it's like, well, why? And it's local. And it's like, why? And it's like, well, local's faster, isn't it? And it's like, well, and it's temporary because our local machine might be go off the air for whatever reason. And the killer one really is copy. We think of this as a copy of data that's somewhere else. And once you realize that it's a copy, you've kind of got to think of what happens if the original changes. So if you were a website and you were selling PlayStations, then you might want to know how many PlayStations you have. And if you've got a copy of the number of PlayStations and your copy is wrong because you've sold one, then you might tell somebody there's a PlayStation available, they turn up and it's gone already, and they're very annoyed, and it goes all over social media and you lose a lot of businesses. So copy can be a bad thing. Alternatively, if it was, say, something like the weather yesterday, what's the weather been for the last week? Well, it's not going to change, so perfectly fine to have a copy. So it's just a kind of facet of it more than anything else. But once you realize that fast is all that matters, today we're going to say, well, why not in the cloud? Why not somewhere else, somewhere far away rather than somewhere close? And once it's in the cloud, if you can access it, other people can access it, other applications, other copies of your application. So we might all have access to yesterday's weather. So what are the kind of features of a cloud cache? Well, it can be huge. The one I'll show today, it could be terabytes. You can share it as on the previous diagram. So that same information can be reused. You can have all the other kind of nice stuff that you might want: persistence, monitoring, management, querying, Security and resilience is a big one as well. You know, just because it's out in the cloud, well, it can be as stable as the cloud is. And you put business data there, so suddenly your cache, don't really have to think of it as transient, it can be permanent. All right, so how would we do this? Well, I'm going to show you Hazelcast, unsurprisingly. So what Hazelcast does, Hazelcast is a memory-based storage that runs across multiple host machines. Now, these host machines today are out in the cloud, but you can have them on premise as well, or on your laptop, whatever you kind of feel like it. And the storage is essentially split across multiple processes, and they're storing it in memory. So if a process has got enough capacity to hold 10,000 data records, and you've got 2 of them, you've got enough capacity to hold 20,000 data records. And if your business volume grows, or you decide to hold more information, you just add another one, and now you've got 3, and now you've got enough capacity to hold 30,000 data records. So there's a kind of cost element that kind of comes under your own control. How many machines? Because machines aren't free. So if you can imagine you were doing something like bank statements. So you go to your online bank, you want your bank statement to be responsively available. You know, what's the last month's transactions? Well, if you're got that in a memory cache, then that's faster. You might not hold all your transactions, you know, years worth of transactions in memory, because you just don't use them. You can fetch them from the disk when you need them. So the kind of key thing there, again, if your bank transactions, they don't change. These are things that have happened. So you don't change them. So you're not kind of worried about consistency. If the disk copy changes, the memory copy gets out of date, well, it doesn't happen. But new transactions come along, so you can increase the cache. But basically, the idea you think of is that this data space is cut into pieces and shared across available processes. If you remember offices and you remember filing cabinets, you might have had a filing cabinet where it had A to M. All the things that began with A, B, C, D were in there, and another cabinet that was N to Z. And you've got 2 filing cabinets, and roughly half your records in one and half are in the other. And if you need to keep more pieces of paper, you add another filing cabinet, and then you rearrange that data so that it's now no longer A to M, it's now A to J and K to P and R to Z or R to Z, whatever. And as I mentioned, you can kind of share that between multiple applications. Oh, sorry. So that's the kind of essence. It's a memory store that you're accessing by some sort of TCP connection. It doesn't have to be physically close, but it can be, or it can be remote. I'm going to run it today partly in the cloud and partly on my laptop, and I believe they're about 1,000 miles apart, 1,600 kilometers, but I haven't measured it. All that matters is speed. So time for a demo. And I'm going to look at this person, Leonardo da Pisa, famous mathematician, more usually known as Fibonacci. I believe that means son of Bonacci, Fibonacci, kind of like a nickname, and in the same sense, I'm Stevenson, son of Stephen. So what he's kind of most famous for is the Fibonacci series of numbers. So basically, you know, the first 2 are both 1. But then in general, each number is the sum of the 2 previous numbers. And it's quite an interesting mathematical problem for some reason, but here we're doing it as a computation, because typically when you think of caching, you're thinking of caching something static, you know, caching a news story or bank transactions. We can be caching the result of calculation, and the cost is in the calculation. So what he was trying to do was model population growth in rabbits. So if you've got 2 rabbits and they breed, they might give birth to 2 more rabbits. So now you've got 1 plus 1 gives 2. That's the first Fibonacci number. The oldest rabbit might die. So now you've got 1 plus 2, and that gives 3 children. Again, the oldest might die. So now you've got 2 plus 3. And if you add them together, that's 5. So that's how the Fibonacci series goes. It goes, you know, 2, then 3, then 5. It goes up non-linearly. And little side point is that's, of course, why the first two numbers are 1, because if you're breeding from rabbits, you can't start from 0. Here's some code in Java. Here's some code in Node.js. We're not really going to look too closely at that. We're going to look at the Python version. But this is just me showing off the show I can write in multiple languages. I can't really, it's only Java. But the Python version is quite succinct, so that's the one we'll look at. So basically, it's a function call. You pass it a number. I want the ith Fibonacci number, the 7th or the 15th or whatever. We do a lookup to that Hazelcast map, that Hazelcast key value store, saying, what do we have anything for number 15? Do we have a record for that? Do we have that result already? That's our cache read. And if we do, we just return it because we don't need to do anything. We know the answer because this is a calculation that is deterministic. And if we don't, this is where we do this. We make a call to ourselves for the previous 2 Fibonacci numbers. So it's 2 recursive calls. And that's the thing that takes the time. So this is an expensive calculation computationally. And then once we have that answer, we have to store it in the cache so we don't need to recalculate it the next time. So that's the put if absent. And the if absent just might be because we've got multiple processes running. Somebody else might have beaten us to it. It wouldn't do any harm to save it twice, but just a little bit unnecessary. So, time for a demo. This demo is running out on the cloud. There's an actual IP address for the demo, 35.195.123.251, port 8080. There's my web app. Now I need to stop my presentation to swap to the demo. But if you go to that URL, you will see a lovely flag-colored Fibonacci series cache browser, and that will update in real time as I do some calculations. So I did mention I'm more of a Java programmer than anything else. So I'm going to start. This is on my laptop, but I'm connecting out on the internet to a port out on the internet where my Hazelcast instance is running. It takes a second or two to spin up. There we go. So I am connected to my Hazelcast cluster, and I have written a little command which I'll call Fibonacci. If I ask for Fibonacci of, well, let's go with 4, then what we will see is it calculates it using a non-caching mechanism and a caching mechanism just to demonstrate the difference. And we have to look up 4, and 4 requires us to look up 3 and 2 requires us to look up 1. So there's the recursive calls, and here's the caching calls, and it looks like there's 5 of one and 4 of the other, so it seems slightly better. Without caching, it's faster the first time because it's not having to probe that cache. But if I run that number again, without caching, it's still pretty fast, but you'll see that the without caching has made a lot of calculations. Run it again. So we're still faster for that small volume to do it locally, but let's take the number up. Let's do 20. And we see the non-caching has made a lot of calculation calls, and the non-caching's taken a second and the caching's taken 16 seconds. Let's try it again. And now we're seeing the non-caching pretty much always takes a second to do 20 calculations recursively, 400, half a second, but the caching version's beating it hands down. And if I change 20 to 21, what we'll see is the runtime just keeps going up and the non-caching version continues to beat it. And if anyone's following my demo on the cloud, we'll see that my cache has populated. So there's the 21st Fibonacci number is 1096, whatever it is. So it's time now to look at a little bit more kind of value in this. So let's have a look at a bit of monitoring. So that one, I can monitor my cache. I'll get the password correct, which I did. That's a good. We're having a good day. No, we're having a bad day. There we go. So if we look at my, so I have a key value store called Fibonacci. It has 21 entries in it, and what we'll see is that there's 9 of them are stored on one and 12 on the other, making 21 in total. So it's stored across 2 machines. Because remember what I said about that kind of filing cabinets in the office, A to M and N to Z. It's not necessarily 50-50 because you're doing it based on chunks rather than individual records. And because this is a memory store, you might be concerned about data loss if one of the processes crashes. So those 12 that are there are also backed up on another one. And if we wanted to see what the Fibonacci numbers are, we can say my map is called Fibonacci. I'm going to do this, and let's just say get me, let's just do all of them. And I'll go and retrieve, here's all the Fibonacci numbers. So number 14 is 377, number 19, 4181. They're not held in series. So there's something that we can now do that you couldn't do before. You can do this querying against cache data that's in the cloud. So that is me using an SQL browser to check data that's been calculated by Java. So just to prove that, I can also check my cache from Java, and you can see all the numbers, and I can clear them out. My cache is empty, and if you're following along on the web and you're on this web app, you'll see that the cache is cleared back down. So that was Java calculating some Fibonacci numbers. What I'll do now is I'll get Node.js to do it. I'm doing this in Kubernetes. So I'm asking Kubernetes to run a Node.js job. And if I do the... this isn't an interactive. This one's just a batch job that goes and does some calculation. But if I look at the logs for it, then what we'll see is starting. But while it's starting, let's kick off some other ones. Let's do create myself. Let's do, I would see it's run because there's the output. We've calculated the first 15. Let's look at the logs. There we go. So that's what it's done. It's calculated the first 15 numbers using cached Fibonacci in Python. We can see that cache is available on the web. If we look from Java, Java can access it as well. If I ask Java to do the 16th, let's go with the 17th Fibonacci number, it only has to calculate 17 and 16 because they're already available out in the cache. So that's Java sharing a cache with Python, not with Python, that was Node.js. So let's do Python. So we've got Python. We can do this calculation for Python. And Python, let's see what it does. So if I attach to my Python process, I can see what Python does. So Kubernetes, you're asking it to create a virtual machine to run that job. There we go, off it goes. And let's do the same idea with, let's just do one more for luck. Let's do Golang. And let's see what Golang is up to. I think I asked Golang for a larger number. Waiting for it to create the virtual machine. So we're already at 25, so there's been some more calculations run. There we go, there's Golang doing some, so it's doing its non-caching version, and it's looking up the first 25, and it only has to go back to number 18 because Java had already calculated number 17. And there we go. So non-caching took a set length of time, caching took a different length of time. So basically what you can do is you can be creating data from one application, sharing it, and doing it from another application. And kind of the key thing that kind of I'm trying to stress here is kind of two things. One is this kind of whole, it's a shared cache. One of the questions you've got to think about with all kind of caches is what's your consistency model? So if you're accessing data and it changes, what happens? On Hazelcast, you've got the choice. You can have it kind of automatically, immediately updating in a synchronous fashion, so you always get the accurate value, or you can have it doing it asynchronously, which is allows it to drift. It comes into line as soon as it can, and that only might be a few milliseconds. But if you're accessing it, you might get the old value, so what you might call a stale cache read. the Fibonacci series, that wouldn't matter because there wasn't changes. If it was, again, coming back to PlayStations, if you were buying PlayStations and you said your shop has got 15 PlayStations and you sell one because you think you've got 15, but in fact you've got multiple web clients and in fact you sell 2, at some point you're going to disappoint the customer, and that's very bad. Conversely, it could be something like a hotel where you're showing the availability of the number of rooms in a hotel. Now there, you want your website to perform quickly because basically people will give up. If they're doing a search for a hotel room and your website doesn't respond fast enough, they give up. So access to the data is important. Accuracy isn't that important. So if you're a hotel and you're showing the wrong number of rooms because you've got concurrent bookings, you might overbook. Now you'll kind of know about it later and you can sort it out somehow. You know, I've had that happen to me. I've turned up at a hotel, it was overbooked. We've rebooked you into a better hotel and they'll pick up the difference. And it's like, yeah, that's a result. So it doesn't have to be an IT solution. I've got kind of 2 more things just to show before I cut back to the slides. So if we do get pods as the Kubernetes terminology to find how many virtual machines they're running, or containers, essentially. I'm running 2 Hazelcast instances there in Java. So that is what's called stateful set in Kubernetes. So I've got 2 running and I wanted 2. So I can ask Kubernetes to change that number. So just while we're doing this, so there's the name. And I want to change it to 3. So now if I do my command, I'm running 2, I wanted 3, Kubernetes will go and find another machine somewhere. If I go to my map and I look at my Fibonacci map, we'll see that I've got 25 records because that was the result of the cache running across 2 machines. At some point very soon, well, hopefully very soon, what you'll see is that number increase. Now it looks like it's gone down, but that's actually because another machine is joined. And what we're doing is we're rebalancing the data on those machines. And very soon we should see that there are in my cluster, how many members? There's now 3 members. So if we look at my map, we'll see my data records are now split this way. So we still have 25, it's just rearranged them, 6, 6, and 13, and the backups are the other way on other machines, not necessarily paired up. So you've got 1 backup, so you can lose a machine. If you had 2 backups, you can lose 2 machines. You really kind of don't want to be losing lots of machines. It means your cloud providers let you down. But all the while, this is kind of happening in the background. Nobody really kind of notices. So the last thing kind of to look at before we cut back to the slide deck is just see the coding. So there's the Golang version of the coding. I think today I said Python was the one we're going to look at. So I've got the same coding in C++ and Python and so on. So here's what we do. So this is the Python version. We're saying, give me a client of Hazelcast, make me a client connection to my Hazelcast cluster. We give it various things. We can give it names and labels and so on. The reason you give it names is if you were on the web and you're doing your monitoring, you can say, you might want to know which clients are connected, and they've all got names and labels. But more importantly here, really all we're saying is what we're going to connect to, and it's a cluster connection in Kubernetes. It's just an IP address. If you see from here, oh, there's the 3rd client, 3rd process joining. If I was to scroll back far enough, or just repeat the command, I'm connecting from, this is my laptop, and I'm connecting out to the internet, so I just give it an IP address and it works the same way. And it just passes through a tunnel into Kubernetes. So my cluster's in Kubernetes and my client is outside. The other ones were inside Kubernetes under Kubernetes control. So you can kind of mix and match whatever you kind of feel like. And that's a big thing for a cache. You can share this all over the place, all over the world, essentially. Now, if we check our stateful set, we see we're back at 3. But so really all we're saying is we're going to create a connection to a cluster, and we're either connected by a Kubernetes address or an IP address or something. And then we're just saying, well, get me a map get me a key value store with a specific name, and we just pass that into our Fibonacci function. So this is our Fibonacci function. So there's the stuff I mentioned before. You're just doing a map get. Is this key in the map? And you get back an answer and you return it. I'm also logging it out the screen, but that doesn't really, not a thing you would normally do. And I'm doing some timing and so on, and results prints. But fundamentally, that's it. And if you were doing it from, well, let's pick another one, Golang. So in Golang, there's a couple of bits. So you're connecting and you're saying my cluster name and addresses. It's the same on all of them. If I'm doing it from Java, Java's got a nice little abstraction called Spring where you just sort of wrap up the function call, and it intercepts the function call and just puts the function input and output in, which makes life even easier. But yeah, you can do it whatever language kind of suits you. And more importantly, it's whatever language suits your organization, because you'll find in a big business that you'll have multiple people in multiple teams, and they'll all have their favorite. So people will be doing it from, will be saying, having some sort of system that's written in Node.js, doing some computation, create some values in a database or whatever. And you've got another system that's written in C++, and pulling it in that database is what's slow. So if you can store it in memory, then you can access it faster, and that's going to make the business more effective. So it's that kind of data sharing between teams. You know, they all have their favorites. So just to kind of recap and kind of wind down on the demonstration, the Fibonacci calculation is computationally expensive because you've got that double recursion, some sort of exponential runtime. If you're doing the caching version, then it's at worst linear. You know, to do the cache of number 50, you only need the number 49 and 48, and but 49 creates 48, so execution time is linear, but if 48 is already there, then 49 returns very quickly. So execution time is at worst linear. But the kind of key thing here is that data isn't stored anywhere else. So this idea if it's a copy is like, no, this is data that you can. So typically with caches, it's about speed, but we're thinking not so much about slow storage, is this data is slow to obtain. And obtain might be a slow store, so you're pulling it from a database that's old and you've had it a while and can't cope with the increasing volume in your business. Or it might be that it's a complex calculation and takes a while to reproduce. You know, might be producing a report or PDF or something, you know, of the day's activity in your business. That might take 20 minutes to recreate. Well, that's a good thing to cache, because then the next time you access it, you can get it quickly. If it's your bank, you can go to your bank's website and you're getting last month's statement PDF there, it's immediate. Now, other ones, if you wanted the month before's statement and that took a few seconds, well, as a user, you know, that's really just a cost decision. You could say, well, let's cache 3 months worth of statements in memory, and then they're very quick on the app and our bank looks good to customers. But you might equally find that customers just don't care about fast access to April's statement. Fast access to May's statement is important, but fast access to April, we hardly ever do it. And if there's a delay, most people are comfortable with that kind of retrieving, and you spin the hourglass. So there was just some numbers I've run. I think the highest we ran today was 25, but I went up to 50, and that took about 50 seconds. You know, I've only got 40 minutes for my talk, so I'm not going to do any higher number. And probably I'll get some sort of Stack Overflow as well if I take a higher number. So there's another consideration, is that the whole thing might just totally blow up your machine. And with caching, the response time is pretty good. 4 milliseconds, 3 milliseconds. I think you saw it there live. Sometimes it was 40, sometimes it was 30. You know, you've got other factors that are going on, because you've got, you know, is this process swapped into memory? Is the connection shared? Is it passing through load balancers? All sorts of things. So it's not ever going to be as fast as a cache that's on the same process, because you've got that network retrieval time. So again, it's just another style of cache that you can think of, and you've just got to be aware of what its pros and cons are. It's going to be faster. It's going to be not as fast as local, but you can still cache locally as well. You can be doing both. You can have two caches. You can have that level 2 kind of caching notion. So you can do that local retrieval. You've just got to, the most important thing to think of is accuracy, correctness, staleness, call it what you like. If you've calculated the Fibonacci numbers and stored them in a cloud cache for other processes to reuse, or you've calculated an overnight report or any kind of stuff for other processes to reuse, you can also safely cache that locally, or given how much space you have locally, you might not be able to cache it all. As I mentioned, the cloud version, you could be terabytes, and you're not going to have that locally. You might only have like a few kind of gigabytes. So you can have a subset, the most important things. And you wouldn't care about that changing. I think back to the hotel availability, you might be caching it locally to make your website respond quicker. And it's not the same as the global availability of hotel rooms in your hotel, but you don't care too much because you can identify that number. You might be caching something like the price of Bitcoin, and that's just totally wrong because you would be doing trading on something that's changing very rapidly and very significantly, significantly in the sense of money. So if you're caching anything that affects your business or affects profitability, you've got to be very careful around how accuracy might drift. So last two slides. Really, well, why not cache remotely? The answer really is you can. Whether you should or not is going to depend on your application. So you can cache remotely. You can see data that is stored somewhere else. And really, that's all that actually data is. You know, when you do a database call to do like a retrieval from some SQL or something, it's the answer you see. You don't actually see that it's stored in the database and it passes through, query engines and so on. You're just getting the output. So really, all you actually ever get is the output of a function. You give it an input and you get an output. And for something like a database retrieval, you're thinking, the value on the database is what you're getting back. But in fact, database retrieval can be doing calculation. You might be doing sum-offs and maxes and so on. So you're always getting back the result of a calculation. Sometimes the calculation is a no-op. But really, if you recognize that what you get back is the result of a calculation, you don't actually see it's come from the database. So swap it to something else and it's a bit faster. Then your business is faster. But, fast is a bit of an obsession, but, does it matter? So execution time is really the thing that matters. Can you make your coding faster so you can support higher load or get your results out quicker than your competition can be? So if you were hotel searching, you're getting results faster, your people are happier. If you're a bank with your bank statements, that's reputational. Your website performs well, people like your bank or don't criticize your bank. So the other thing you got to think of is money. So this is storage. Storage is not free as hardware. Everything I showed today is open source Hazelcast. There are bits we will sell, but this caching is not free because you've got the machine somewhere and you've got the cloud provider and all those other things. So it's that trade-off of execution time versus money. You could keep all your data in memory or a subset in memory and page it in from disk and just do that on a kind of cost-benefit kind of basis. So you can work out what are the things you're going to need. And there's things you can do with caching, which I haven't kind of shown today, where you can kind of expire out items that you don't read. So if you've got something that you put in the cache and then haven't used it, you can discard it from the cache after a certain amount of time or when you're low on memory or whatever. And then you don't have it. And then you have the cost of recreating it because that's how caches work. And it's the cost of recreating it, calling some function that retrieves it from somewhere else where it's stored. And kind of, this is a kind of another thing is maybe caching isn't the right word. Maybe we're just saying we're querying a store. it's a store that's in memory that can maybe fetch it from a store that's on disk, and the store that's on disk can maybe fetch it from a store that's on a tape, and the store that's on a tape can somehow fetch it from a paper copy. You'll find in most businesses, data is duplicated in lots of places, so it's kind of difficult to know where the kind of golden copy is. Where is it really coming from? Which one changes and the other one's following suit? So it's a copy of that data, and it could be your only copy, because if you can recreate it, then you don't need to store it elsewhere because storage costs money. But the one really to focus on is that staleness. Does it matter if the data changes? So the example I did today, it didn't matter, but there are other examples where clearly it will. So that's it. That's the summary. I'm just about to end the slides and go to the kind of Q&A, but just the last point, there's my email address, neil@hazelcast.com. We've got about 5 or 10 minutes for questions, or less than 10. So Q&A time, I'm going to end my slide deck and go back to there we go, there's the thank you. Stop sharing and go to live Q&A. So, does anyone have any questions? Someone's bound to have questions. So while I'm waiting for a question to come in, I did that in 5 languages. There was some Golang, some C++, some Python, some Node.js, and Java. I'm kind of most familiar with Java. The Hazelcast storage systems or storage processes, those are Java. So that's a Java process that's storing data, but you can connect to it from other languages. And if you're a Java developer, then you'll find that very easy. And for other languages, you'll find that they're common primitives. So there's things like maps, which is what I showed you. You've got topics and queues and atomic counters and so on. And there's an implementation of the Raft algorithm around the concurrency primitives to make sure that they are correct. Because if you've got things like atomic counters, you want them to have the right answer. So again, it comes back to what level of correctness can you tolerate? Because it's always a trade-off of speed versus correctness. And that's what caching is all about. Questions? Nobody? So just to kind of fill in then, so that was a 3-node Hazelcast cluster. So that was 3 processes running in the cloud. I ran a couple of hundred last year. So, you can scale up as you like, scale down. You saw me doing it while it was live. So again, that kind of scaling is another thing you want to think of, because that's part of the cost model of cloud, is that if you're caching information and it's a busy period, so it's like something like Cyber Monday, Black Friday, heavy trading day, you can increase your capacity, and then when it gets quiet, you can decrease your capacity. And these kind of events like Cyber Monday, it's not going to be a surprise when it is. I can tell you when it is, just by looking at my phone. It's like towards the end of November. So it's a Monday following the 3rd Thursday in November. So that's a busy day. So maybe that weekend you would add some extra machines, or maybe a few days before, because there's going to be capacity increases. And how that works nicely on the cloud is typically you build per usage. So if you're busier, you're getting more money coming in, your IT costs go up, that's fine. If you're doing it kind of on premise, then to scale to extra machines, you've got to have those machines, you've bought them. The rest of the time, are they sitting idle, or can you reuse them? Much kind of harder. Yeah, so that's it. I mean, you basically ask your cloud provider for some more machines. If it has them, you get them, your capacity goes up. Five minutes to go. No one? No one in the chat room? So really, speed is what you obsess about, not locality. You can have a cache yourself on your process and other people, difficult to access, certainly shared memory. If you're running on multiple machines, there'll be firewalls and zones and all sorts of stuff. As long as you can make a connection from machine to machine, just like a ping, then you could have your cache on the other machine or on other machines. And And then if it's on multiple machines, I mentioned that backups thing. If one machine fails, then you've got the backup copy. And if you've got that synchronous updates on, which is the default anyway, then the backup copy was matching the primary copy. So you don't lose data and you don't lose correctness. You can choose to lose that correctness if you want. You can choose to lose data. You might say, well, let's have no backup copies, because if you've got 1 million records and 1 million backups, that's 2 million, and that costs on storage. And how likely are your machines to fail? Hopefully not likely, because hopefully you've got good machines. So then you might say, well, actually, because we're just caching data, we can retrieve somehow, either from that database or from that recalculate the result, then we'll not bother having a memory backup. So we've only got 1 million records rather than 1 million plus 1 million copies. So our storage footprint's halved, and that's financial cost. And it's all just a trade-off. You might say, actually, let's have 3 copies because we're super obsessed with being able to access this data quickly, and we also expect our machines might fail occasionally. Kind of in my mind, that's the wrong answer, but if you expect your machines to fail, you should change your machines, but sometimes that's how it works. Am I back? Oh, sorry, I clicked the wrong button there. So I'm back in the room.